Unit 8, Lesson 2, Exploring the Logarithmic Function. In this lesson, which was exploring the logarithmic function, we started by graphing the exponential functions of 2 to the x and 1/2 to the x. We then took the inverse of these functions by switching x and y, graphed that, and then discussed its properties, leading us to define the inverse of any exponential, a to the x. The inverse of this, which is x equals a to the y, we can rewrite as y equals the log base a of x, right? And so this is what we'll come to define as the inverse function of a to the x. These are inverses of each other. We call this the logarithm base a to the x. Logarithm base a of x. You can kind of see the logarithm of x to the base a, or log base a of x, right? And so this could be log base 2 of x, could be log base 1/2 of x, could be log base 7 of x, right? The same way exponential functions could have whatever base you want, logarithms could have whatever base you want. And so let's talk about the properties of this thing. The y-axis serves as a vertical asymptote to the logarithmic function, while the x-axis serves as a horizontal asymptote for the exponential function, right? Exponentials kind of look like this. Logarithms will kind of look like that, right? The domain for the exponential function is xer, while the range is all the positive numbers, yer, such that y is greater than 0. And as we know about inverses, the domain and range switch between the function and its inverse. So the domain for the logarithmic function is xer, such that x is positive. The range for the function is yer. Which leads us to the biggest tool that we have in this unit. If x equals a to the y, then y equals log base a of x. We will use these not only to help us write inverses, but to help us evaluate logarithms. And so let's write a couple inverses here. The inverse of y equals 1/5 to the x, right? We can start by just switching the x and y if we wanted to, right? X equals 1/5 to the y. But this is where we're going to invoke this switch of exponential and logarithmic form, right? This is the exponential. This is the logarithmic. This is where we can switch it, meaning that y equals the log base 1/5 of x, right? These two are equivalent. They're both the inverse of y equals 1/5 to the x. But eventually we'll start to make this a little bit quicker, right? What's the inverse of log base 4 of x? Well, it's 4 to the x. What's the inverse of log x? This one's tricky because we don't see the base. And we define when we don't see the base, it's really log base 10, right? And so the inverse of log base 10 is 10 to the x. And the inverse of 5 to the x is log 5 of x, right? So the base now becomes the subscript, and x is now, the subject of the log, right? Going back and forth between exponential form, right? So the way I'll say this is the base stays the base, right? 7 was the base, it stays as the base. What was in the log goes by itself. What was by itself goes to the log. So x equals 7 to the y. That's the same statement, right? These are equivalent. It's not like we took any sort of inverse. It's just we rewrote this in exponential form. What about this one? Well, the base here is 10, so the base is 10. What was by itself is in the exponent. What was in the log is by itself. This one, base stays base, x and y switch. Base stays base, x and y switch, right? There you go. Evaluate each of the following. So there's a couple different ways you can do this. I'll show you kind of the more traditional way first. The traditional way is writing this in exponential form, right? So the base stays base, y goes into the exponent, 49 goes here, right? This is just rewriting it in the exponential form. And now we're essentially solving an exponential equation. We can rewrite 49 as 7 squared, and then we get 2 to the y, right? Because a 7 to the something is 7 to the something. The somethings must be the same. However, there's kind of a few lines happening here. And can we make this a little bit more efficient? Well, we can. And we do that by asking ourselves, okay, what is the logarithm asking? The logarithm is asking, what exponent do we have to put on 3 to get 81, right? And you might know this, and maybe you know that it's 4. And so here's actually the more efficient way of writing it. We can just replace 81 with 3 to the 4, almost the same way we did with 49 in the first example. But now, look at what we're asking now. What exponent do we have to put on 3 to get 3 to the 4? That's just 4, right? And now we can solve it like that. So here we can rewrite the square root as a 1/2 exponent. What exponent do we have to put on 6 to get 6 to the half? It would be a half. Same thing here. What exponent do we have to put on 4 to get 1/16? Maybe this one isn't as clear. So let's rewrite 1/16 as 1/4 squared. Now maybe this is a little bit more clear. It's 4 to the -2, and so y is -2. Right, so some more simple evaluating, and lesson 4 is going to be much more about evaluating, and so we'll keep working on this. The main skills we should be practicing are writing inverses, and then going back and forth between exponential form. All right, and just knowing when to do each one. Inverse means you're switching x and y. You're switching x and y. Writing in exponential form just means what wasn't a log is now going to be in the exponent. You're just invoking this clause that I circled here. You're not changing anything. You're not taking any inverses. You're just rewriting an equivalent statement to the one that you're given. All right. So that's kind of the gist on exploring the log function. In the next lesson, we'll learn how to evaluate this thing with some more complicated equations.